Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking a little bit about freefall motion. So at this point in the semester, we should already, or you should already have watched the video about motion with constant acceleration. So you can recall from motion in 1D with constant acceleration the following equations. First, we have the position versus time equation. The position I'm denoting with a y here because we're sort of like moving vertically, and in 2 dimensions usually you use a y for that. And so oftentimes we'll use a y even if it's a 1-dimensional motion for the vertical component. Oddly enough, when we go to 3D, then usually that vertical component becomes z. But we don't have to worry so much about that in this course. Second equation of interest is that the velocity as a function of time is the acceleration times time plus the initial velocity. And third, we have essentially what happens if you combine these two equations by sort of like solving this one for time and then substituting into this one and combining like terms, which is more of a scalar equation. Delta y times 2 times the acceleration is equal to the final speed squared minus the initial speed squared. So those are the sort of 3 relevant equations for 1D motion with constant acceleration. What we are adding to all of this today is freefall acceleration or freefall motion. Essentially what that means is that the motion takes place under the influence only of gravity. As we will learn in a future lecture set or a future video, gravity in this case is basically the force that is influencing the motion, and that in turn controls the acceleration of the motion, and all other parameters basically then are contingent on that acceleration. So let g represent the free fall acceleration, or sometimes also called gravitational acceleration. So we usually just replace the acceleration in these terms or in these equations by this free fall acceleration g. Near the surface of a planet, the free fall acceleration is constant. So, and it may depend upon where near the surface you are as to what that constant is. For example, on the Earth, we have mountains, we have valleys, the Earth is slightly oblate, the Earth is spinning, and all these things have some effect on our free fall acceleration. But to 2 digits, we have the same value. So near the Earth's surface, g has a value of 9.8 meters per second squared. And how near do you have to be to the Earth's surface? Well, you need to have a little more background in forces and gravitation and so on to get that, but if you're within a few miles of the Earth's surface, this 9.8 meters per second squared number basically is correct. Typically, so for most of you in the US who might be watching this, if you want to go out another value, g is about 9.80 or 9.79 something for most in the US. There are some places where the value can even be as high as about 9.81. but we will typically use this right here. Most of the 9.79 values actually round up to 9.80. Most of the 9.80 values typically round down, but they can be a little higher and a little lower. So we'll typically use 9.80. This is, of course, in meters per second squared. If you go somewhere else, like the moon, the local free fall acceleration, we could call that like G moon, is approximately 1/6 of G for the Earth, where G for the Earth is these numbers. Another commonly used one on Mars. So if you go to Mars, then G for Mars is about 1/3 G for Earth. Now typically, again, we're going to be doing problems here near the Earth's surface, but these are, if you wanted to go to another planet or to the moon or so on, you get a different value. If you go to a bigger planet like Jupiter, then G is a lot higher than on the Earth, although you also have a much, much denser atmosphere on Jupiter. On Venus, where it's just a little lower than the Earth, you have a much denser atmosphere, etc. So that wind resistance is a lot more substantial at a much lower velocity. And so I don't know the extent to which it's fair to say you have free fall near those planet surfaces. But on the moon, there's no atmosphere. On Mars, there's a very thin atmosphere. And even on Earth, the atmosphere is thin enough that until you get to a pretty good speed, you can neglect air resistance and buoyancy and so on. And this works out pretty well for your free fall acceleration. There's different ways to measure free fall acceleration. I don't really want to go into all those in today's video because it'll get very long, but one common way is to basically construct a simple pendulum and plot the length of the pendulum versus time, and the slope of that line will give you the local free fall acceleration. We also have obviously devices that can just measure acceleration directly. What are the equations for motion with free fall? So equations for motion, 1D, of course, we're not to 2D motion yet. Basically, you have a bit of a choice in how you want to define things. We usually like to define up as positive and down as negative. So we take up is positive, and in that case, our free fall acceleration, and again I'm using for the Earth's value, would be represented by negative 9.8 meters per second squared, or 9.79 meters per second squared. It is negative because it's downward, and it's downward throughout the motion of the object. So if I have somebody who has like a ball and they toss the ball upward, then we could take like the ball at different points in the motion as it's going up and as it's coming back down, and we could draw what is the velocity doing and what is the acceleration doing. So here the initial velocity is basically up, and it's getting slower and slower and slower, and there's like no velocity here at the top, and then it's down and getting bigger and bigger and bigger. So this is the velocity of this object. If I want to do the free fall acceleration for the same object, the free fall acceleration at all times would be like this. Here's G again, G again, again, and notice that they're all basically the same length and they're all oriented downward. So G is not varying through this motion. Up here, I might have G is negative 9.8 meters per second squared, and also at the same time, V is 0. So these are the numbers we might use to represent G and V at this location. And of course, this is the top. This is the top. Somewhere else, V may be larger or larger and negative, but G remains negative 9.8 meters per second squared. Okay, the equations, therefore, might look like this. Y could be negative 1/2 G T squared plus V initial T plus Y initial. So put kind of simply, we could take the negative sign away if we put a vector sign over it, but if we're trying to represent it with numbers, this would look like negative 1/2 of 9.8 meters per second squared times the time, plus whatever, let's say like plus or minus V initial time, plus or minus Y initial. And so the commentary here is moving up initially, and then this right here would represent starts above 0, and then this right here would be if moving down initially. And then likewise, the other thing, the other minus sign, is if it starts below 0 meters. Okay, but this one right here, this right here is negative 4.9 meters per second squared regardless. Of course, it has to be on Earth. Okay, so that is like the basics of freefall motion. We could also write the other equations, like the final velocity is G times T plus the initial velocity, and so that would be represented as negative 9.8 meters per second squared times the time, and again plus or minus the initial speed, depending on if it's going up or down. Maybe we should have a very quick example to close. All right, here's a typical example for a freefall motion, fairly simple example, in which you have a ball that's being thrown straight up with an initial speed of 19.6 meters per second. We want to know how high it goes above where it's been thrown from and at what time it gets to that point after having been thrown. This is a typical way of these problems being worded, by the way. There is the courtesy neglect air resistance on here. Sometimes that's left off, in which case you kind of assume you're neglecting it unless told otherwise. And the other thing that's generally assumed with these problems is that you are standing on the Earth somewhere when this happens, and so your free fall is 9.8 meters per second squared. So let's figure out what that final height is. We call that maximum height delta y max, and it happens to have the property that the speed will be 0 at that time. That's again going back to this diagram. At the top, the speed will be 0, or at least the vertical component of the speed is 0. Our relevant equation is this one, and again this term is 0 if we're looking for the maximum speed. Plug some numbers and solve for delta y max. You get this equation. The numbers look like this. Gives us 19.6 meters. For time, we use this equation. Plug in numbers and we get approximately 2 seconds. Alright, and that's it for today's video. We've had this brief example. Hopefully it helps you understand the topic as well. And thanks for watching.